Yeah, thank you. Thank you very much, Javier, for that very kind introduction, and of course for the invitation. And of course, many thanks to all of you attending this seminar. It is a great pleasure to give a talk at this institute, and I hope that I can do so physically also one day. So my plan over the next 40 to 45 minutes is to introduce this fascinating phenomenon that is hydrogen embrittlement, and then elaborate on how we have developed a mechanistic multiphysics understanding and modeling framework to predict fractures assisted by hydrogen. But before I start, let me say that there are a lot of people that have contributed significantly to what I'm about to show. Not only the PhD students in my group, the Mechanics of Infrastructure Materials at Imperial College London, but many other collaborators around the world. I have listed in the slide the ones that are particularly related to the results that will be shown today. So let's get started. First things first, what is this hydrogen embrittlement phenomenon and what is so special about hydrogen metal interactions? Well, we know since more than 100 years ago that metals are very sensitive to the presence of hydrogen. As you can see in the slide, Johnson wrote in 1875 in the Proceedings of the Royal Society about an extraordinary and remarkable decrease in fracture toughness and breaking strain in iron and steel in the presence of hydrogen. And in those days, you will very rarely see words such as remarkable or extraordinary in scientific papers. But how hydrogen degrades metals is indeed remarkable and extraordinary. One of these effects of hydrogen in metallic materials is how the ductility reduces significantly with increasing the amount of hydrogen. You can see here uniaxial stress strain curves. And if we introduce hydrogen into our specimens, for example, by exposing them to hydrogen gas, then we see a very strong reduction in the failure strain. Another important effect is the drastic reduction in fracture resistance. You can see in the slide that with increasing hydrogen content, we go from a fracture toughness of roughly 150 megapascals a square root meter to a fracture toughness that easily goes below 40 megapascals a square root meter. And this is a low strength steel. In high strength steels, the reduction in fracture resistance can be of up to 90%. And this is a very important point to emphasize. The susceptibility to hydrogen damage increases with the strength of the steel. You can see here a plot of fracture toughness versus material strength. This is for a given hydrogen concentration, typical of exposure to seawater. And you can see that high strength steels yield a fracture toughness that is below 10 megapascals a square root meter, almost like a ceramic. And this figure has two important implications. One is that hydrogen is effectively compromising decades of metallurgical research. We have developed high performance materials, but we cannot use them. And the second one is that high strength steels very significantly widen the range of environments where hydrogen is problematic. With these more susceptible modern materials, very little hydrogen content is sufficient to trigger failures in many applications and sectors where we never heard about before. So before high strength steels were developed, hydrogen embrittlement was mostly a problem related to aggressive environments, for example, those typical of offshore structures in the energy industry. However, high strength steels are very cost effective and we want to use them for our buildings, bridges, railways, cars. And this is triggering numerous hydrogen fracture problems across the defense, transport, and construction sectors. And in otherwise benign environments, you can see an example in this newspaper article where hydrogen embrittlement is bringing structural integrity problems to one of the most famous skyscrapers in London. And last but not least, hydrogen could be the solution or one of the solutions to our energy crisis. We already have hydrogen fueled cars, trains, and buses in the market. We have a number of these in London. And you can imagine how problematic it's going to be to store and transport hydrogen to power all those vehicles. So given the magnitude of the problem, you may wonder how can it be that almost 150 years after Johnson's paper in the Proceedings of the Royal Society, the problem is not only unsolved, but hydrogen-related accidents are becoming more and more frequent. Well, one of the reasons is because it is a very challenging phenomenon that crosses the boundaries of mechanics, chemistry, and material science. We do know some things, of course. We do know that hydrogen atoms enter the material, diffuse through the crystal lattice relatively fast, and are attracted to areas of high hydrostatic stress or high volumetric strains, where the lattice expands and there's more space for the hydrogen to accumulate. But then in that fracture process zone, hydrogen interacts with materials in many different ways and at multiple scales. So the physical picture is quite complicated. For example, at the atomistic scale, hydrogen can reduce the bonding strength between metal atoms. Hydrogen can also stabilize vacancies. Hydrogen can change the dislocation mobility, and so on. And this lack of scientific understanding comes, of course, at a great cost. Two recent examples are the failure of bolts in the San Francisco Bay Bridge, with a repairing cost of $45 million US, and the cracking of pipelines in the Kashagan oil ridge with a repairing cost of $3.6 billion US. So this is a massive amount of money. So I think that hydrogen embrittlement is a very beautiful problem because it is scientifically very challenging and very fundamental, but at the same time, it has very strong and direct implications for society and engineering practice. So as an engineer and a scientist, I find very rewarding to work on these kind of problems. So I aim at tackling this long-standing challenge of developing a predictive model for hydrogen embrittlement, and I divided my efforts roughly into 4 research fronts. First, it is important to precisely characterize the stresses ahead of the crack. And this is not only relevant because brittle failure will occur at a critical stress, but because, as I mentioned before, hydrogen accumulates in areas of high hydrostatic stress. The second research front involves gaining mechanistic understanding of what is hydrogen doing at the fracture process zone. And this is another key step because hydrogen interacts with metals at many different scales and in many different ways, as I mentioned before. So we will never be able to model a wind turbine atom by atom. So the challenge lies in separating first order effects from second order effects and incorporating those key ingredients into our models. I think that is a big challenge for a material scientist or a mechanician. And third, of course, we not only want to get the physics right, but we also want to get the chemistry right. We want to know precisely how much hydrogen we have, where, and when. And last but not least, we want to couple all of those ingredients into a computationally robust framework that not only has the proper physics and the proper chemistry, but also the capability to deliver predictions at scales relevant to engineering practice. And I feel that this is very important to address these challenges on the computational side as well, because I have the personal ambition of enabling virtual testing in the energy sector and in hydrogen-sensitive applications in general. As you know, virtual testing saves a lot of money these days to the automotive and aerospace industries. They mostly crash cars and computers nowadays. And extending this vision to more challenging areas where the environment compromises the durability of materials requires not only a deeper material science understanding, but also the development of sophisticated computational schemes. So let me elaborate a bit on these 4 research fronts. So I will start first with this key aspect of the importance of resolving properly your crack tip stresses. And the key step here, or I guess in any research problem, is to identify what are the critical variables of your problem. In this case, hydrogen concentration and stresses, and also what is the critical length scale. There's an obvious trade-off between computational cost and precision. We're still very far away from being able to use discrete dislocations or atomistic approaches to model real components. But if all the interesting things are happening in the first 3 atoms ahead of your crack tip, then your efficient continuum model is not going to have enough resolution to resolve the physics of the problem. So I guess the question here is, what is the critical length scale for hydrogen embrittlement? And we can determine the critical distance at which cracking occurs by interpreting experiments. So hydrogen-assisted fracture is a little bit like fatigue, in that if you plot the crack velocity versus the applied stress intensity factor, you get this 3-stage region. A first stage immediately after cracking, where the crack speed grows fast with applied load. A stage 2, where the crack speed is insensitive to the remote load. And finally, the rupture. And the reason why the crack speed is constant in the stage 2 is because crack growth is diffusion limited. You have enough mechanical driving force, so to say, but you need to wait for the hydrogen atoms to reach the critical distance ahead of the crack. So cracking is intermittent here. the crack does small jumps as the hydrogen atoms reach the critical distance. And since we know how much time it takes for hydrogen to travel a certain distance, d, for a material with a diffusion coefficient capital D, then we can use experimental data to determine what this critical distance and what this critical time is. So for example, in the case of this nickel superalloy, we can see that the stage 2, this is the stage 2 crack growth. The stage 2 crack growth crack speed is in these 3 replicate experiments at minus 1,000, at a potential of minus 1,000, gives us a value of 0.04 microns per second. And since we know the material diffusion coefficient, we can measure that independently. Then we can basically come up with a very simple system with 2 equations, the crack speed and the 1D diffusion analogy. And then we can see that the critical distance, by solving this very simple system of 2 equations, we can see that the critical distance equals 1 micrometer. So the hydrogen atoms travel for 1 micron ahead of the crack before reaching that critical region. So back to the drawing board. What methods do we use? At the microscale, ideally, we need discrete dislocation dynamics. But since we want to impact engineering practice, we are constrained to use continuum models. So the alternative that we have explored is to enrich our continuum models with the physical effects that you're missing at the critical distance of your problem. That means we introduce the physics implicitly, so to say, by changing your constitutive equations. So you can compare what your continuum model predicts at a micron ahead of the crack tip with what discrete dislocations predict, for example, and then when you see the difference, you can enrich your continuum model. And the main effect that you're missing out at 1 micron ahead of the crack tip is the dislocation hardening mechanisms associated with plastic strain gradients. This has been consistently observed in a number of microscale experiments from indentation to bending, but the ones that I like more are the torsion experiments by Fleck and co-workers. What you see in the slides are experiments done on thin copper wires, torsion on the left and uniaxial tension on the right. And you can see that in uniaxial tension, where strains are uniform, the response is roughly the same independent of the size of the wire. However, in torsion, where plastic strain gradients are present, the flow strength can be 4 or 5 times higher for thinner wires than for thicker wires. So you have geometrically necessary dislocations that develop to accommodate the lattice curvature, and this leads to a stress elevation. Of course, if I were to try to capture this size effect using conventional plasticity models like von Mises plasticity, I wouldn't be able to do so because there's no length scale in the constitutive equations. But the good news is that many clever mechanicians, some of which are listed in the slide, have devoted their efforts to extend plasticity theory to small scales by developing what are called strain gradient plasticity formulations. The general idea in these formulations is that the plastic work or the flow strength is related not only to the plastic strains, but also to the plastic strain gradients. In that way, a length scale comes naturally into the model due to dimensional consistency. And one can quantitatively capture those dislocation hardening mechanisms that you see when you have large gradients of plastic strain confined into a small volume. You can see it here, the finite element analysis of the torsion wires that I showed you before. And my contributions here have been on 2 fronts, mostly. One, in the development of robust computational schemes, as these strain gradient plasticity theories are typically higher order, involving higher order stresses or conjugate to gradients of plastic strain. And consequently, there are some challenges associated with the numerical implementation. But also I've been working mostly in applying these strain gradient theories to gain insight into crack tip mechanics. Because if you have a crack in a specimen, independently of the size of the specimen, you're going to have a plastic zone that is physically small and that contains strong spatial gradients of deformation. So you're going to see those local hardening mechanisms that we saw before, the same way you see them in indentation. And now and today you can measure very precisely G&D densities ahead of cracks and inclusions. And what you see when you model crack tip fields with the strain gradient plasticity is what you see in the slide. So here I'm plotting the tensile stress versus the distance ahead of the crack tip. And you can see that far away from the crack tip, both conventional plasticity and strain gradient plasticity agree. But as you approach the crack tip within tens of microns, strain gradient effects start to play a role, and then you get a stress elevation as a consequence of those local hardening and strengthening mechanisms. And differences are quite significant if you look at a 1 micron ahead of the crack tip, which is the critical distance for hydrogen embrittlement. And let me remind you that getting these stress levels right is very important, not only because of purely the cohesion or brittle fracture arguments, but also because the higher your hydrostatic stresses are, the more hydrogen will accumulate at that critical distance. And in passing by, let me just say that in a way, this is what you see when you use discrete dislocation dynamics. You can see in this is from Bill's Corten's group, you can see here that fracture is attained at critical cohesive strengths that are up to 9 times larger than the yield stress. So this is much higher than the maximum stress levels that you predict with conventional plasticity models. And this stress elevation has allowed us to not only bring some insight to the hydrogen embrittlement problem, but also to rationalize many brittle processes that occur in the presence of plasticity. Because the theoretical lattice strength or the cleavage strength are the order of 10 times the yield stress. So you need higher stresses coming from somewhere in order to rationalize from a mechanistic point of view these brittle processes. For example, we had a lot of fun with this approach, and we look at fracture of B-material interfaces where you also can model dislocation pileup, and also developing statistical frameworks for low temperature cleavage of ferritic materials. But let's go back to the hydrogen problem. And now this takes me to the second research front, which involved gaining mechanistic understanding into the process. And the key question here is to understand, how does hydrogen make metals fail in a brittle manner, often with the crack propagating along the grain boundaries, as you see in that slide. For this purpose, I tried to determine what were the first order effects between the ductile to brittle shift that we see in the presence of hydrogen. I came to the conclusion that 3 ingredients are key to develop a mechanistic rationale. The first one is that atomistic calculations show that the bonding strength between metal atoms is reduced with hydrogen occupancy. You can see here a DFT result of surface or fracture energy versus hydrogen occupancy. This is for nickel. And you can see that if we have enough hydrogen, if we're on this side of the graph, then the cleavage strength or the grain boundary strength will be much weaker. And there has been a bit of a discussion in the atomistic community in regards to quantifying how strong this effect is. And a big part of the controversy relates to figuring out how much hydrogen you actually have. So where are you in this x-axis, this hydrogen occupancy? And so that is the next research question. So where are we in this hydrogen occupancy axis? How full of hydrogen, for example, are our grain boundaries? And the answer comes from the well-established mass diffusion laws. Specifically from Moriani's equilibrium, you can relate the hydrogen concentration in the crystal lattice, which is the y-axis here, with the occupancy of a trap, this theta t, as a function of the binding energy of the trap. And what we learn here is that the strong traps, such as grain boundaries, with an absolute binding energy that is 40 kilojoules per mole or higher, will be essentially full for hydrogen concentrations as low as 0.3 ppm. So if you go here in this graph, you will see that as long as you reach any meaningful value of the lattice hydrogen concentration will give you a full occupancy of the trap, or almost full occupancy of the trap. And this is what you see in experiments. So this image is taken from a recent atom probe tomography study. And you can see how this grain boundary, the red region, is full of hydrogen atoms. So our grain boundaries are definitely going to be weaker. And then when you properly consider the stress level near the crack tip, you see that the drop in cleavage strength is sufficient to trigger brittle fracture. Or in other words, when you combine the fact that the hydrogen will drop the cleavage strength, let's say by 20%, with the fact that your stresses at the critical distance are going to be close to the cleavage strength, maybe 9 times the yield stress, as we saw in the DDD simulations, then you end up with a mechanistic model that can predict the ductile to brittle shift as a natural byproduct of the simulation without any ad hoc criteria or fitting parameters, because you don't have stresses or energy that is big enough to hit the cleavage strength, but the moment hydrogen comes into the pictures, you are able to naturally predict that. And I will show this later. So let me jump to the third research front, the chemistry. Hydrogen diffusion is normally characterized using an extended version of Fick's law, as you see in the slide. Note the important role of the hydrostatic stress, as I mentioned before. So there's a strong coupling with the mechanics. And one thing that we have been working on is in the development of multi-trap models, as hydrogen atoms can be trapped at microstructural features such as grain boundaries, dislocation, carbides, and this affects diffusion. So it's something that you may want to incorporate in your modeling depending on what you're looking at. And another important aspect that has to be addressed to properly quantify hydrogen is to adequately characterize hydrogen ingress into the metal. This is not complicated for gaseous environments. One can just make use of Siebert's law, but in aqueous environments, the physical picture is more complicated. And what I've been working on with Alan Turnbull is in developing generalized boundary conditions that can resolve the electrochemistry diffusion interface. And I won't elaborate much more on this for the sake of time, but what can I say is that one thing that I can say is that what we learned using these rigorous formulations is that the usual procedure of prescribing a constant hydrogen concentration can be very inaccurate. So it's worth taking that into consideration. And I think this is a key aspect of the modeling that sometimes it has been overlooked, maybe because we are more familiar with the mechanics side of it rather than the electrochemistry. But we need to take into account that almost every model there, almost every chemomechanical fracture model for hydrogen that is out there is very sensitive to the hydrogen ingress. So the input to the model, which is the hydrogen concentration. And so we need to be able to properly figure out how much hydrogen is actually coming in. And one more thing on the diffusion side before I move to the fracture process. Remember that mechanics plays a key role. There's a hydrostatics term here. And in fact, for the steady state case, this is the closed form solution for the lattice hydrogen concentration. And you can see that there's an exponential dependence on the hydrostatic stress. That is why it's so important to enrich continuum models to be able to accurately quantify crack tip stresses. In fact, as you can see in the slide, experimental measurements of hydrogen concentration ahead of the crack tip agree better with the predictions from strain gradient plasticity and show two effects. The first one is that hydrogen content increases with the remote load, which is only captured with strain gradient plasticity. And second, then the hydrogen content increases as we approach the crack tip, which again, you can only capture if you enrich your continuum model. So that takes me to the fourth research front, fourth and last one, which has to do with the development of compelling multiphysics computational tools. And myself, I have used a variety of computational fracture mechanics approaches in the past, like XFIM or Quisitson models. But not so long ago, I came across the phase field fracture method, and basically I cannot speak more highly about it. The idea of these phase field methods is to use an auxiliary variable to track the evolution of interface boundaries, which is a well-known mathematical and computational challenge. With the phase field paradigm, we follow the interfaces implicitly, so to say, in the sense that we no longer have a sharp interface, but the auxiliary variable, so-called phase field or phase field order parameter, is telling us where the interface lies. So the method was first developed in the microstructural evolution community, where the change in shape and size of microstructural features, such as grains, can be predicted by defining the evolution of the phase field in terms of other fields, such as temperature, for example, through a thermodynamic free energy. And in fracture mechanics, the phase field tracks the crack solid interface, taking, for example, a value of 1 in the crack phase and of 0 in the undamaged material points, and varying smoothly in between. So the temporal evolution of the phase field is then described by a differential equation that can be easily solved using standard numerical methods. And this makes the tracking of evolving interfaces computationally tractable. You can see in the slide how complex cracking morphologies can be captured, such as crack merging, nucleation from arbitrary sites, branching. So it's a very powerful tool from a computational perspective. So at this point, you might say, okay, all good on the computational side, no issues dealing with evolving interfaces such as cracks. But when do those cracks propagate? Or in other words, what differential equation do you use to evolve the phase field? Well, one of the nice things about phase field models is that they provide a computational framework for Griffith's energy balance. So those of you familiar with fracture mechanics will remember that Griffith, one of the fathers of the field, postulated that a crack will grow if the energy released by the solid reaches a critical value, this so-called critical energy release rate or material toughness. This energy balance is a result of considering, in a thermodynamics context, the work required to create two surfaces. And one can formulate Griffith's energy balance in a variational form with a term accounting for the stored elastic energy in the solid, as given by the strain state, and a second term characterizing the fracture energy, the energy dissipated by the formation of a crack. Therefore, crack nucleation and growth can be predicted naturally without ad hoc criteria, as dictated by the minimization of this energy conservation statement. However, minimization of this Griffith functional is hindered by the fact that the crack surface gamma is unknown. But here is where phase field comes to our rescue, because one can use the phase field as a marker, transforming the surface integral into a volume integral and enabling us to solve this global minimality problem. And there's two things that I want to emphasize here. First one, following standard continuum damage mechanics arguments, the phase field can be thought of as a damage variable that goes from 0 to 1. So 0 in intact material, 1 in fully cracked material points. And as a consequence, by increasing this value, it reduces the stiffness of the solid, as you can see here in the first integral. And secondly, there is a gradient term and consequently a length scale. So the model is non-local, which ensures mesh subjectivity. So results are mesh independent as long as you resolve this phase field length scale. So at the end of the day, we have a model that is physically sound based on Griffith and the thermodynamics of fracture, and at the same time computationally very compelling. You can get a good overview of the model by looking at the balance equations. The first equation is the solution to the deformation problem, the standard balance of linear momentum with the phase field degrading the stiffness of the solid, which increases with mechanical straining. And then the second equation is the phase field evolution, sort of a competition between the toughness of the material, constant material property, and then the strain energy density, so the energy that is stored in the solid. So just by solving this simple system, we can predict in both 2D and 3D very complex cracking patterns, such as branching, merging, initiation from arbitrary sites, complex trajectories, and without convergence issues or the need for reimmersion. For example, in this slide, you can see crack branching due to the application of a dynamic load. Red color contours denote crack material points, or the areas where the phase field equals 1, so cracks basically. And we have had quite a lot of fun with it and contributed to the phase field scientific community by presenting new solution schemes and by using new phase field formulations for fracture and fatigue, and developing new phase field formulations for fracture and fatigue in functionally degraded materials, in shape member alloys, and also in fiber reinforced composites. So it has been a great experience, to be honest, working with this method. Results are mesh independent, the method is easy to implement, and there are no convergence problems. So how does hydrogen come into the picture? Well, let me remind you of the three balance equations. There's one for the displacement field, with the phase field degrading the stiffness of the solid like a damage variable. There's one phase field evolution law, which is sort of a competition between the strain energy density of the solid, which changes with the strain state, and the fracture energy. So whenever you have enough energy stored in your solid, your crack will grow. That's consistent with thermodynamics. And then you have a hydrogen transport equation with hydrostatic stresses driving diffusion. So how do we couple the fracture and the hydrogen parts in this problem? Well, the big picture is very simple. What we know from experiments is that hydrogen reduces the toughness. So we just need to make our critical fracture energy or material toughness depending on the hydrogen content. How exactly does hydrogen degrade the material toughness? Well, that's the big question, I guess. And of course, each of us might have a different answer. The good news is that the model is universal in that it can accommodate any mechanistic interpretation. The key idea is that you have a material toughness that, in the absence of hydrogen, we know very well. We can characterize it with a fracture experiment. And then in a hydrogen-containing environment, you can introduce what we call a degradation function, here called F, that can be dependent on any mechanistic parameter that you consider relevant. It could be the lattice hydrogen concentration, it could be the total hydrogen concentration, it could be the hydrogen trapped in grain boundaries, it could be the dislocation density, any macroscopic or microscopic parameter that you think is involved in the fracture process. And of course, one can also come up with empirical laws by fitting experiments. In our case, we want to follow the rationale that I outlined before. So we establish a direct quantitative connection with the atomistic calculations that I discussed before, which tells us how the surface or the fracture energy is reduced with hydrogen coverage. So we can run atomistic calculations offline and use them to define a degradation law that has no fitting parameters. For example, in nickel, based on these DFT calculations, you can define a linear degradation law where this variable chi is the hydrogen damage coefficient, which equals 0.41. So there's nothing really to fit there. The hydrogen diffusion will tell you how big the theta is, and then you get automatically the variation of the fracture toughness. And this is a similar approach, I must say, to the one championed by Michael Ortiz in cohesive elements. And in phase field models, there's a direct connection between the phase field length scale and the strength and the toughness. You can see it here. So that if you run a one element model, you get the following stress strain curve. which resembles acquisitive zone traction separation law. So that if you consider the role of the hydrogen, then what you can see is how the strength diminishes as you increase the hydrogen concentration. So that's what you get there. And one last comment on the coupling between the phase field and hydrogen. One thing that you should consider if you want to capture precisely the crack propagation stage is the fact that the environment, the hydrogen gas or the aqueous electrolyte, will probably occupy the newly created crack surface. So you need moving boundary conditions for the diffusion problem. You can see in this video that in the context of phase field fracture, one can use a penalty approach to readily capture how the hydrogen concentration and the environment, so how the hydrogen concentration of the environment basically follows the crack as the crack propagates. So now let me show you some representative results obtained after coupling all the ingredients. So we have the microscale plasticity model, we have the mechanistic interpretation based on offline atomistic calculations, we have a rigorous treatment of the diffusion and the diffusion boundary conditions, and then we also have the phase field fracture to deal with complex cracking phenomena. So the first result that I'm showing here, these are R curves, so crack growth resistant curves. So the applied K is in the y-axis, and then the crack extensions in the x-axis. And as you would expect, the model captures how increasing the hydrogen content, you bring down the refractory resistance. What you see in this slide are the results obtained for different loading rates, showing how the model captures another well-established experimental observation. The faster the loading rate, the higher the crack growth resistance. And what I'm showing here is the effect of GNDs, one could argue, and the associated dislocation hardening mechanisms. Because we know that these strain gradients or extra dislocation gradient mechanisms will become more prominent what we see here is that these gradient effects become more prominent when the material toughness is smaller, because the size of the fracture process zone, R naught, is smaller. And as a consequence, the ratio of the plastic length scale, which is a fixed material property that you can fit to a microscale experiment, and there is roughly on the order of 5 microns, that ratio is going to increase because this is a constant property, and then the fracture process zone, the region over which you have the gradients, is going to be smaller. And this is something that is also expected. We know that gradient effects are smaller in ductile fracture processes, where the critical distance is farther away from the crack tip, and the fracture process zone is large. And here you can see how the crack growth resistance changes with the material strength. And this is important to showcase how our model can naturally capture the shift from ductile to brittle fracture once hydrogen comes into the picture. Because for each value of the strength, you can compute a steady state fracture toughness where the R curve becomes flat, so this region here. And we know that brittle interfaces such as grain boundaries have a strength on the order of the theoretical lattice strength, so 10 times larger than the yield stress approximately. So we can plot the steady state fracture toughness as a function of the acquisitive strength, and then we get two curves depending on whether we have hydrogen or not. In the absence of hydrogen, the role of plastic strain gradients is small, and consequently the stress elevation is roughly 4 times larger than the yield stress, much below the cleavage strength. So brittle interfaces will not fail. So you have a ductile fracture process. However, when hydrogen comes into the picture, it reduces the toughness, and consequently the fracture process zone, leading to the red curve shown in the figure. And you can see that this is enough to predict the brittle factor of interfaces once you take into consideration the small reduction in strength that you get with hydrogen content, as we see in the atomistic calculations. So you can find more details of this rationale in the papers, but the key thing that I want to emphasize is that the model can naturally capture the change from a ductile fracture prediction to a brittle one once hydrogen reaches the fracture process zone. Or in other words, the combination of strain gradient plasticity, interface strength degradation due to hydrogen, and a fracture process zone model provides a modern rationale for the so-called hydrogen enhanced decohesion mechanism, in my opinion. So let me move on to show a few representative quantitative comparisons with experimental data. For example, what you see in the slide is a comparison with tensile tests on pre-charged notch steel bars, showing a very good agreement in terms of failure stress versus the pre-charged hydrogen content. Here you see a set of interesting experiments where notch duplex stainless steel samples were held at a constant load in a seawater bath. Each sample is subjected to a different constant load, and all of them fail at a relatively early time from an engineering perspective. But what we can do with our model is not only to reproduce the experiments, but to run simulations over very large timescales so that we can determine the critical stress below which engineers can load their structure safely. And we have also used this virtual tool to gain insight into the suitability of a standardized tests, specifically in regards to slow strain rate tensile testing. We learn, as our experimentalist colleagues in the University of Virginia suspected, that early cracking occurs, and this compromises the suitability of what is arguably the most widely used experiment for hydrogen, for measuring hydrogen susceptibility. And one can also use this tool to simulate any kind of experiment, minimizing expensive experimental campaigns. So for example, bolt cracking is a big problem in hydrogen embrittlement. And here you can see an STM experiment to measure the strength of a steel screw anchored in a concrete slab, which is anchored to a concrete slab. And this is a problem that involves also contact between two materials, as you can see here. The complete failure of the screw, as you can see in the slide, can be captured in our virtual experiment. So one can really precisely and effectively run those virtual experiments. And these agreements with experiments gave us the confidence to go beyond the lab into field applications, aiming at enabling the virtual testing paradigm that I mentioned before for hydrogen sensitive applications. And these are a couple of toy examples. The first one deals with a crack propagating from existing pits due to corrosion. And the second example simulates crack propagation in lifting equipment made of a high-strength steel. But more excitingly, we can model large-scale 3D problems and correlate our models with inspections, creating a digital twin of critical infrastructure. Here you can see a pipeline containing multiple defects due to pitting corrosion that has been characterized by La Rosa and co-workers using non-destructive evaluation. It is a 12-kilometer pipeline, and we choose to model a critical section of 3 meters that contains more than 100 defects. We are not I think a key point to emphasize is that we're not limited to model cracks, but we can also model defects of any arbitrary geometry. And once you know that in these phase field models, because you are solving for the damage variable, so to say, as a degree of freedom, it is very easy to introduce those defects. You just need to assign an initial condition to the nodes located in the damage area, and then you can load at the in-service conditions to predict when failure will happen. So you can use the same mesh for all pipelines, no matter how many defects there are. And this is shown here, how the pipeline starts being loaded. And you can see soon at the top here how defects start growing, how they eventually merge, and finally how they lead to the complete structural failure of the pipeline. And this looks a little bit like a video game, but I should emphasize that it's a sophisticated multiphysics model. Everything is computed on the original finite element mesh in an implicit backward Euler scheme without any convergence issues and fully parallelized such that it can run in a few hours. So we have a tool that allows us to know how cracks will propagate and when they will propagate, such that we can decide when to replace the component or what are the limit service conditions. Finally, and this is ongoing work, we have extended the framework to fatigue. The key idea is to include a fatigue degradation function, this red F here, and one can then predict, based on the material toughness and nominal material properties, Paris law coefficients, and also you can compute virtual SN curves for any geometry. For example, in the figure here, you can see that the role of hydrogen in reducing the number of cycles to failure for a notch bar. And I emphasize here that the Paris law behavior and the SN curves are an output of the calculation, they are prediction basically, not an input, because this is quite different from other existing models. And I'm going to end this talk just by showing very briefly another exciting avenue of research, which is the use of phase field modeling to capture how the surface of a corroding metal evolves. So localized corrosion is generally a problem of great interest to our community, to the hydrogen embrittlement community, among other reasons, because hydrogen can be produced in corrosive environments. However, predicting corrosion damage is a massive challenge for scientists and engineers. In fact, as you may know, the vast majority of the research conducted in this area is experimental, as it has been long considered to be a too complex problem to model computationally. One of the biggest challenges from the computational side is capturing how the aqueous electrolyte, you can see it here, how the aqueous electrolyte solid metal interface evolves. You can see in the video, which is a synchrotron analysis of corrosion in stainless steel, and you can see how pits form, how they interact, and under certain conditions transform into crack. So capturing how this aqueous electrolyte solid metal interface changes in time is one of the biggest drawbacks that has held our computational capabilities in this problem. But this bottleneck can be tackled if we exploit the phase field paradigm and implicitly track the evolution of this electrolyte metal interface. The differential equation that you solve for the evolution of the phase field is more based on models for phase field models for solidification rather than the fracture models that we discussed so far. But I won't get into the details for the sake of time. You can find them in a recent paper. I will only say that we have also incorporated into the modeling the influence of mechanics in corrosion kinetics and also the film repassivation and rupture process. And these are just some representative examples to show how the model can capture pitting corrosion and the pit to crack transition in both 2D and 3D. And we have validated our model predictions with experiments showing a very good agreement. So let me just finish by providing some concluding remarks. I would just say that developing models for predicting hydrogen embrittlement is indeed challenging, but I think that this elusive goal can be tackled if one considers first enriched continuum models such as strain gradient plasticity that can calculate precisely crack tip stresses at a few microns ahead of the crack tip, which is the critical distance for hydrogen-assisted fracture. Secondly, a mechanistic line of thought to rationalize the ductile to brittle transition is needed. And we came with one by coupling microplasticity with atomistic calculations and well-established laws of hydrogen transport and equilibrium. And finally, or thirdly, by appropriately estimating the hydrogen content, so using rigorous models for hydrogen transport and interface reactions. And the fourth ingredient is developing compelling multiphysics computational tools that will allow you to deliver predictions that can be benchmarked against experiments and inspections for which we use the phase field fracture method. And the good news is that once you put all those ingredients together, then things seem to be working nicely. And you can see, you have seen that we have been able to get a good agreement with experiments, that we also been able to predict fracture and fatigue, not only in lab conditions, but also in complex engineering applications. And finally, we have shown that the phase field paradigm can also be exploited to model another long-standing challenge, which has also important technological implications, which is corrosion damage. And I think that we will see a revolution in this area similar to the one that we're seeing in fracture mechanics. That's all. Many thanks, of course, to my research sponsors, to the industrial partners that have supported us in one way or another, and of course to all of you for your attention and patience. Note that I release all my codes in my website, so feel free to download them, play with them, and email me if you have any questions. Thank you very much.